Today we're doing a deep dive into one of the most elegant papers in generative modeling, the Variational Lossy Autoencoder, published at ICLR 2017 by Chen, Diederik, Kingma, Tim Salimans, and colleagues from UC Berkeley and OpenAI. This paper addresses a fundamental tension in generative modeling. Autoregressive models like PixelRNN and PixelCNN are exceptionally powerful density estimators, but they lack structured latent representations. Variational autoencoders learn meaningful latent codes, but when you pair them with powerful decoders, the latent variables are simply ignored. VLAE provides a principled framework to resolve this tension, giving us explicit control over what information the latent code captures, and achieving state-of-the-art density estimation in the process. Let's start with a critical observation that the paper formalizes. Consider a standard VAE. We have an encoder Q of Z given X, a latent code Z, and a decoder P of X given Z. The evidence lower bound, or ELBO, decomposes into an expected reconstruction term minus the KL divergence between the approximate posterior and the prior. Now, here's the problem. When the decoder is a powerful autoregressive model, say an RNN or PixelCNN, the conditional distribution P of X given Z factorizes as a product of P of X underscore I given Z and all previous tokens X less than I. Since RNNs are universal function approximators, this autoregressive decoder can represent any probability distribution over X, with or without dependence on Z. So what happens during training? The model discovers it can avoid the KL divergence penalty entirely by simply setting the approximate posterior equal to the prior. The latent code carries zero information, and all the modeling capacity flows through the autoregressive decoder. Previous work attributed this to optimization challenges, but the authors argue this is a fundamental property of the objective itself. To understand why the latent code gets ignored, the authors appeal to bits-back coding, an information-theoretic framework for variational inference. The idea is to view a VAE as a two-part code for data compression. First encode the structure Z from the prior P of Z, then encode the residual details of X from the conditional P of X given Z. The receiver decodes Z, then decodes X, and can also recover additional information from the approximate posterior Q of Z given X. The expected code length under bits-back coding is exactly the negative ELBO. Now, the key insight. The lower bound on the expected code length is the Shannon entropy of the data, plus the expected KL divergence between the approximate and true posterior. Since this KL term is always non-negative, using the latent code always costs at least some extra bits. This gives us the information preference property. Any information that can be modeled locally by the decoder P of X given Z, without access to Z, will be encoded locally and only the remainder will be encoded in Z. When the decoder is powerful enough to model everything locally, Z is simply not used. This is where the paper's main contribution emerges. Rather than fighting the information preference property, the authors exploit it. The idea is deceptively simple: design the autoregressive decoder so that it cannot model the information you want the latent code to capture. Concretely, for images, they construct a PixelCNN decoder with a deliberately small local receptive field. The conditional distribution becomes P of X underscore I given Z and X in a window around pixel I. If the window is small enough, say a 3x3 patch, the decoder can only model local statistics, textures, edge patterns, noise. But global structure, like the overall shape of an object or the identity of a digit, requires long-range dependencies that cannot be captured within a small window. By the information preference property, this global information is forced into the latent code Z. The result is a principled lossy compression. Z captures global structure while the autoregressive decoder handles local texture. You control what's lossy by tuning the receptive field size. Let's see this in practice on MNIST. The authors train a VLAE with a 6-layer PixelCNN decoder using filter size 3, which limits the receptive field to a small local patch. The converged model has an expected KL divergence of 13.3 nats, corresponding to about 19.2 bits per image. Compare this to a standard VAE with a factorized decoder, which uses 37.3 bits in latent code per image. VLAE achieves much lossier compression. Looking at the visualization, each pair shows the original image and a random decompression from VLAE's lossy code. The digit identity is perfectly preserved, 4s remain 4s, 3s remain 3s.
But the local statistics are regenerated fresh, the binary masks differ, stroke widths vary slightly, and pixel level details change completely.
This is exactly what the theory predicts. The lossy code captures what the local decoder cannot: global digit structure.
The story becomes more nuanced with OMNIGLOT, a dataset of handwritten characters from many writing systems.
Here, the lossy code sometimes fails to preserve character semantics because OMNIGLOT has more meaningful variation at local scales than NIST. This highlights a critical point: you must design the decoder's limitations to match your specific data and task. The CIFAR 10 experiments make this beautifully explicit. By varying the pixel CNN's receptive field from 4x2 up to 7x4 pixels, you see a clear gradient.
With the smallest field, the lossy code preserves detailed shape and color information.
With the largest field, only rough shape is retained. And here's a clever trick: by making the decoder operate only on grayscale versions of the local context, you can force the latent code to encode color information specifically.
This gives researchers fine-grained, explicit control over what their representations capture. The second major contribution addresses a different source of inefficiency. Even with lossy codes, the mismatch between the approximate posterior Q of Z given X and the true posterior P of Z given X wastes bits in the bitsback code. To reduce this gap, the authors propose parametrizing the prior distribution P of Z as an autoregressive flow. Starting from simple Gaussian noise epsilon, the flow F transforms it into a structured latent code Z equals F of epsilon.
Each flow step is implemented by a made network, with the transformation Z underscore I equals sigma underscore I times epsilon underscore I plus mu underscore I, where sigma and mu depend autoregressively on the previous latent dimensions.
The key mathematical insight is striking: rearranging the ELBO reveals that using an autoregressive flow prior is equivalent to using an inverse autoregressive flow posterior along the encoder path.
But along the decoder path, the AF prior provides a deeper generative model P of X given F of epsilon, while IAF posterior provides a deeper encoder. Since both have identical computation cost at training time, the AF prior gives you a more expressive generative model essentially for free.
The experimental results are comprehensive and impressive across the board. On statically binarized NIST, VLAE achieves a negative log likelihood of 79.03 nats, beating the previous state-of-the-art IAF VAE at 79.88. On dynamically binarized NIST, VLAE reaches 78.53, again the best result. But the most dramatic improvements come on other datasets. On OMNIGLOT, VLAE achieves 89.83 with fine-tuning, a massive improvement from the 106.31 of a standard VAE. On Caltech 101 silhouettes, the gap is even more striking, VLAE at 77.36 versus the previous best SPARN at 88.48, an improvement of over 11 nats. Remarkably, these results use the same hyperparameters across all binary datasets, tuned only on statically binarized NIST. The appendix ablation table confirms each component's contribution. Adding a Gaussian prior to the pixel CNN decoder reduces NLL from 87.55 to 79.48, and switching to an AF prior further reduces it to 78.94. For natural images on CIFAR 10, the architecture scales up significantly. Latent codes are represented as 16 feature maps of size 8x8, with the prior being factorized Gaussian noise transformed through 6 autoregressive flow steps, each implemented by a 2 hidden layer pixel CNN with 128 feature maps. The decoder is a conditional pixel CNN++ with 4 blocks of 64 feature maps and gated ResNet connections. The authors test both ResNet and DenseNet variants for the encoder-decoder backbone. DenseNet VLAE achieves 2.95 bits per dimension, the best result among any variationally trained model, and competitive with the best purely autoregressive models like Pixel CNN++ at 2.92.
They also introduce soft free bits, a smooth variant of the free bits technique that blends KL annealing with free bits to stabilize training on this challenging dataset. The generated samples show coherent objects with natural textures, demonstrating that the model has learned meaningful latent structure.
Let's step back and consider what VLAE contributed to the field. 3 things stand out.
First, the bits backcoding analysis of the information preference property gave the community a principled understanding of when and why VAE latent codes are used or ignored.
This resolved years of confusion about optimization challenges in VAE training.
Second, lossy codes via receptive field control provided an explicit mechanism for representation engineering, an idea that influenced subsequent work like VAEs' discrete bottleneck and the design choices in modern hierarchical VAEs like NVAE. Third, the autoregressive flow prior demonstrated that expressive priors can be practically beneficial, paving the way for the rich prior distributions used in modern latent variable models. The paper's own forward-looking note anticipated extensions to temporal data like audio and video, and to semi-supervised learning. The core principle, that you can control representation learning by deliberately limiting decoder capacity, remains influential in the era of latent diffusion models and beyond.